Hello everyone, welcome to the latest lecture session. We've been discussing mass balance, and before we dig further, let's have a quick recap of what we discussed in the previous session. Mass balance, we are trying to understand what's happening to the mass in a particular system or a reactor volume or a control volume, right? Why are we doing that? Because we are dealing with wastewater and water, and we have different unit process where we remove different kinds of compounds, let us say. For example, in the activated sludge process, we try to remove the organic content, mostly the dissolved organic content, which is our waste, let us say, right. So, how do we do that? We have the mass coming in or the wastewater coming in, and the treatment occurs in this tank, and then the waste leaves the system, treated waste leaves the system. So, to be able to design, let us say, what the volume of this particular tank, or how much time the water has to spend in this tank, right, and also how much or how many microorganisms I need to maintain in that tank, right. I need to be able to understand the aspects in terms of mass balance, right. Mass coming in, mass going out, yes, and what is happening to the mass within that particular system. That will give me an idea about the accumulation with time, right, or accumulation of the compound in that particular system. In that context, we looked at 3 ideal case reactors. Let us just have a quick recap. So, the first thing is the batch reactor, where we had no mass coming in, no mass going out, but continuous stirring, right. And for that case, we see this is what it ends up to be. If my rate of formation of a compound is 0 and rate of loss is, for a first order reaction, let us say my A goes to products and the rate constant is K, rate of loss is K times concentration of A, right. So, if I plug that in here, what will I get? I will get dC by dt is equal to minus rate constant times concentration of A. Again, C here is nothing but the concentration of A in this context. So, d concentration of A by dt is equal to minus the rate constant times concentration of A. Integrate and so on and so forth. What will I get? I will get, if saying that this is, I am going to represent concentration of A by T, Ct. So, Ct by C naught or initial concentration is equal to e to the power of minus Kt, right. And again, this is the case for batch reactor, and then when we have no rate of formation of the compound and we have the rate of loss to be first order loss, let us say first order, right. So, that is what we have, and this is what we came up with. If we have rate of formation and such, you will plug it into this equation and you will transform the equation. And then we moved on to looking at the other 2 ideal reactors, continuously stirred tank reactor and a plug flow reactor. Let us just have a very quick recap about them. Continuously stirred tank reactor or completely mixed flow reactor. What is it that they mean? First, we have flow coming in and flow going out, and then we have continuous mixing. For the same case, at steady state, again at steady state, and assuming that there is no rate of formation and rate of loss is first order, we came up with this equation, right. C is equal to this particular term here, right, where Ci is equal to C in and C equal to C out. So, let me just play around with this equation just a bit more. I should have done that last time. So, C out, which is this, by C in is equal to, and if I divide by Q here, what will I get? I will get 1 by 1 plus V by Q into the rate constant. But V by Q, we know that we represent it by theta, hydraulic retention time. For example, what are the units out here? V is volume, flow rate is how much volume is coming in per time, right. So, these are more or less in units of time. What is it that this time is giving me now? Practically, what is it that I understand from this hydraulic retention time? It tells me how much time this water or the compound of concern which is dissolved in the water is spending in my reactor, right. That is an aspect that we need to note and which we take into when designing. So, it is equal to 1 by 1 plus k theta. Again, please note that this is the case when we have CSTR at steady state, no rate of formation and rate of loss is first order, right. If it is a different case, obviously you will have to get at a different aspect. And then we moved on to another ideal case reactor, a plug flow reactor. Plug flow as in there is no mixing within the reactor and whatever comes in does not mix with the packet that's preceding and succeeding that particular packet or plug, let us see, flows as a plug. Whatever I put in just flows through like this and goes through, right. So, that is what we have. So, for plug flow reactor obviously we can't use this particular equation, the one that we have been looking at until now, the macroscopic mass balance equation. Why is that? Let us just take a look. Why can't I use this V dC by dt is equal to Q in C in minus Q out C out plus volume into rate of formation minus rate of loss. Why can't I use this? First, this is the mass coming in and mass going out of the system, and then reactions occurring here and so on and so forth. So, let us say if I want to write the rate of loss as Kc, okay, Kc let us see for first order loss. So, what is C here? Because the concentration of my compound within the reactor is not uniform, it is changing, right. Within the reactor the concentration is changing. So, it is not the same within the reactor. Obviously, I can't use it the way we have out here, right, the equation I mean. So, we as an alternative we looked at our fundamental mass balance equation and assuming that advection is only in one direction, right, advection u dc by dx x direction, and assuming that there is no dispersion and or diffusion, right. Ideal case reactor, what did we have is equal to rate of formation minus rate of loss. At steady state this term turns out to be 0, yes. So, u dc by dx, but what is x by u, right, that is again if you multiply it by cross sectional area a into x by a into u, what will that be? More or less it is hydraulic retention time, volume by flow rate, right, hydraulic retention time. So, dc by d theta is equal to rate of formation minus rate of loss. Again, as you can see here we see that this equation tells me that the concentration is changing with distance, right, that is what is taken into account here. Some people erroneously write this equation for plug flow as dc by dt. So, that is a huge blunder. Why is that? For example, this is Haridwar and downstream this is Roorkee and the Ganga canal is flowing in this direction. If I want to look at the change in concentration or understand the system, so what do I need to do? I either need to just sit at Haridwar and take the sample at 9 am, 12 am, 12 noon pardon me and 3 pm and so on and so forth, and then I will get an idea about the change in concentration with time. But I can't say I will take a taxi and I will take a sample here and I will take a sample here and then I will end up at Roorkee at let us say 1 or 2 hours later and take the sample here, and by comparing the samples at these different locations I can't say that or give any idea about how the concentration is changing with time. We will only be able to give an idea about how concentration is changing with distance, but that too poorly because at the same time time has also changed it. So, if you want to look at it you have to take a sample at 9 am I guess at the same time and you will understand how the concentration is changing with distance. So, the point I am trying to make is you either have to keep the space constant when you are trying to measure the effect of time or the variation of concentration with time, or you have to keep the time constant when you are trying to measure the effect of or how concentration changes with distance, right. So, that is one aspect to keep in mind, and as we saw with the fundamental mass balance equation we can get this pretty easily, dc by d theta equal to rate of formation minus rate of loss, and we see that it is relatively similar to the equation for a batch reactor, dC by dt equal to my rate of formation minus rate of loss. But for better understanding, we are going to look at this equation and try to apply that for the plug flow reactor, right. So, plug flow reactor, this is what it is. Yes, plugs which do not mix with each other. So, let us say this is what I have, right, and let us say the distance here from 0, if this is 0, let us say this is x, and the thickness of this particular plug, right, within which I am assuming that the concentration is the same as dx, the thickness is dx, let us say, right. So, now instead of applying the mass balance over this entire section, we will be applying it over the small section that we have out here, let us say, within which we are assuming that the concentration is uniform, because we are only considering a small plug, right, within this plug flow reactor. Yes, we can assume that the concentration with that within that particular plug is constant. So, what is it that we have? We know that our mass balance equation is V dC by dt. Accumulation term, how is my compound changing within the reactor or accumulating, is equal to mass coming in Q in C in minus Q out C out plus volume into rate of formation minus rate of loss. Mass coming in and mass going out, and rate of formation and rate of loss. Please note that C out, we should not what do we say, confuse that with C naught, let us say, right. So, that is confusing depending on the way I write it sometimes. Q I is Q in, Q out here is Q naught here. Let me write it as OUT for the sake of understanding here, right. Q out and C out, fine. So, here what is my volume now? Assuming that the area, cross sectional area is A, the area will be A into dx, not area, pardon me, volume is A dx, dC by dt is equal to Q coming in and Q going out, I am assuming to be the same. So, I will just use the term Q, and concentration coming in at distance x. So, Cx minus Q out and Q are the same, and concentration going out meaning at x plus dx distance, right, Cx plus dx plus volume which is A dx into rate of formation minus rate of loss. So, dividing by this particular volume which is A dx, I have dC by dt is equal to Q by A dx Cx minus Cx plus dx or x dx, let us say, this is what I have, right, plus rate of formation minus rate of loss. So, that will be equal to what now? So, Q by A will be, Q is the flow rate, right, volume per time, and here we have cross sectional area. So, we will end up with velocity of flow of the fluid in the numerator, and we will have here Cx minus Cx plus dx by dx plus rate of formation minus rate of loss, right. So, what is it that I end up with? So, I will end up with minus u, this term is dC change in concentration with distance, right, minus though, right, because it is not Cx plus dx minus Cx, but the other way around, that is why the negative term plus rate of formation minus rate of loss, right. So, let me just write this equation in the next page, dC by dt is equal to this particular term, and what do we have? We had dC by dt is equal to minus u dC change in concentration with distance plus rate of formation minus rate of loss, right. And if I bring this term out to the left hand side, dC by dt plus u dC by dx is equal to rate of formation of the compound minus rate of loss of the compound. So, if you look at it, this is nothing but what we have or what we derived from the fundamental mass balance equation, when we assume that there is no diffusion and dispersion and that there is flow only in one direction. This is what we had earlier. Let me just go back and point that out. I believe right here, this is what we had, the fundamental mass balance equation, and we came up with it, right. or we looked at it or solved it out here, right. So, we can use or go from the macroscopic equation to the fundamental mass balance equation too, or the mass balance equation such that it is suitable to be applied to the plug flow reactor. Again, as you can see now, we now understand why you can't directly apply this macroscopic mass balance equation to the plug flow reactor, right. So, this equation, as we did earlier, if it is at steady state, this term concentration does not change with time, or no variable will change with time, steady state. So, what is it that we have? U dc by dx, u by or x by u, pardon me, is equal to theta, hydraulic retention time. So, what will I have? dc by d theta is equal to rate of formation minus rate of loss. Assuming that its rate of formation of a compound is 0, rate of loss is based on a first order degradation reaction where compound A is going to products and rate constant is K. It is equal to K times concentration of A, right. C is nothing but concentration of A here. So, what will this equation turn out to be? dc by d theta is equal to 0, rate of formation is 0 minus K C. So, C at any theta will depend upon C in or C, okay, I will write C in coming into the system into e to the power of minus K theta. Again, this is the same or not same, similar to what we had earlier, C T by C naught or C in equal to e to the power of minus K T. This is for the batch. So, you can compare the similarity out here, right. So, that is what we have, and until now we looked at applying the mass balance equation when we had mass coming in and mass going out and such, right. So, let me look at what else I have out here. So, until now what did we look at? Let us say this is my relevant system, mass coming in, mass going out. I want to design this system, as in what is the volume, how much time do I need to let my water stay in the system, and so on and so forth. And one example, not one example, some aspects that I want to mention here are that CSTR or completely mixed flow reactor can be used to model, what can I say, lakes, I guess, which we are assuming to be well mixed. Not a great assumption, but not a very poor assumption for some back of the page calculations. Plug flow reactor, what can I use it for? I can use it for, let us say, canals where the turbulence is relatively less or such, let us say canals or rivers, let us say. Again, not a great assumption because we are talking about ideal reactors here, but you understand where it is or what it is that I am trying to hint at, let us see, right. So, let me move on and try to compare different aspects out here. So, here I asked the TA to plot different sets of data. So, here we have plug flow reactor, and this is the case when the system is at steady state and rate of formation is 0 and rate of loss is equal to K C, right. So, this is more or less based on C theta by C n is equal to e to the power of minus K theta. So, for a random K and random units day inverse and obviously day. So, K theta will be dimensionless, yes, K theta will be dimensionless. I plotted the student plotted the relevant data here. So, first what do we see? This is the one with rate constant of 0.1, this is the one with rate constant of 0.5, and this is the one with rate constant of 1 day inverse. I mean, it can as well be any units out here, but these are the rate constants we chose here, let us see, right. And what do you see? Obviously, because the rate constant is less, in this case the green colored one, we see that it takes longer, as much as 25 days for 90% removal to take place, right, 0.1 by 1 or approximately 90%, let us say, right. So, that is what you see, but with, let us say 5 times faster, right, 90% is achieved within I guess around 5 days, 90% removal is achieved within 5 days, and compared to 0.1, if it is 10 times faster, 1 day inverse, 90% is achieved I guess within 2.5 days. Again, it is exponential obviously out here. So, you see the role of the rate constant, right, in deciding the rates of the reaction. And why is this important? Let us say for your wastewater treatment process now. During some summer, the temperature is high, rate constant, which is dependent upon temperature and pressure, will obviously be affected by it. So, within reasonable limits, we will look at these empirical values later. The rate constant will increase with increasing temperature. During the December period or during the winter months, the temperature comes down, at least in Roorkee it comes down to, let us say 6, 7, sometimes 2, 3. So, the temperature decreases. So, obviously, the rate constant will decrease. Why is that an issue? Let us say during summer we have this profile, and during winter we have this profile. It will not change as drastically though, but there will be considerable change or some change rather, if you do not see to it that the temperature is more or less maintained. But in general, sewage has some temperature, so it should not be a great deal of issue in India. So, in winter obviously the performance can be affected depending on how you design the system and how you run it, right. These are the aspects that come into play. So, let us move on and look at the CSTR or the completely mixed flow reactor. So, CSTR or completely mixed flow reactor. So, same case we took K to be these 3 values, and for CSTR what is the relevant equation for rate of formation is equal to 0 and rate of loss is equal to Kc or first order loss, and at steady state what is it, at C theta by Cn, right, is equal to 1 by 1 plus K theta. So, for this what do we have? We see this, right, profile, obviously the lower rate constant, right. So, thus it is going to take more time, that is what we see, to achieve a certain rate of removal when compared to the one with the higher rate constant, right. So, again that is the profile is similar to that of the plug flow reactor. But if I move on and try to compare the plug flow reactor and CSTR for the same rate constant of K, and for the same case when rate of formation is 0 and it is a first order loss A going to products, let us say I am trying to model the concentration of A, C theta by C naught. So, here to achieve, again blue is plug flow reactor, right, to achieve 90%, let us say it takes around, I guess assuming that 0.1 by 1 I guess is 90%, right, or approximately that. So, we see that it takes around 4.5 days, right, 4.5 days. But for a CSTR, as you can see, it takes much longer, as in even after 10 days we see that 90% has not been removed now, right. So, that is something for you to see or not see, think about. Why is it that for the same theta, right, for the same theta, right, theta is V by Q. So, if the flow rate is constant, when we say this theta is the same, what is that means? From the same volume, let us see, right, flow rate coming in is, let us say, the same for the plug flow reactor and your CSTR, and when we say theta of the CSTR is the same as theta of the plug flow reactor, what does that more or less mean? For a given flow rate, the volume is also the same. So, for the similar volume, why is it that while almost 90% is removed by 4.5 days, let us say it is only, what is it now, we still have considerable fraction left, let us say, right, I guess 70% or so is left, not left, pardon me, 30% or so is left after 4.5 days for CSTR. Why is that? So, these are questions we need to understand. Let me see if I have some graph here. Okay, let me try to draw it out here. Again, taking that line of thought further, if C theta by C naught ratio is 0.5, the ratio of theta to achieve the similar level of removal is this: completely mixed by plug flow, hydraulic retention time with a completely mixed flow reactor divided by the hydraulic retention time with a plug flow reactor. We see that the ratio is higher, or what does it mean? It takes more time with the completely mixed flow reactor. Yes. And what do we see if it is by 0.1? We see it is more, and 0.01 much more, and greater, and so on and so forth. The concentration, not concentration, when we compare the CSTR and plug flow reactor, we see that CSTR takes a lot more time. Why is that now? Let us understand the system here. So, we have our CSTR here and we have the concentration coming in, let us say at 150 milligram per liter. Let us say this is BOD at 150 milligram per liter, BOD 5 days, let us say. We will look at what BOD 5 is in the next session, and 150 milligram per liter is coming in, and let us say my discharge standards now into the river or such are 10 milligram per liter. So, what is it that can go out? It can only be 10 milligram per liter. But in CSTR, what is the whole point is that it is continuously mixed or completely mixed. So, whatever is coming in 150 will have to be immediately diluted to a very low value, which is 10 milligram per liter, right. Why is that? Because whatever is in the reactor is what is leaving the reactor, and if I want to achieve a low outlet concentration, the concentration of the compound within my reactor also has to be 10 milligram per liter or the very low value. But why is that an issue? Why is that an issue? Because think of the rate. What will be the rate of loss of this particular compound A if it is going from A to products, right? What is the rate dependent upon? It is A is dependent upon, not A, the rate is dependent upon the concentration of A, right. And here we see that the concentration of A is pretty low, because that is what we want to achieve. If the concentration of A is low, what does that mean? The rate of loss of your particular compound is also going to be pretty low. And before we finish our thought, let us compare it with the plug flow reactor. This is the plug flow reactor. Here it is coming in at 150 and here it is going out at 10 milligram per liter BOD, right, 150 milligram and 10. But is the concentration of the reactor throughout this, compound throughout this reactor the same? It is not. We know that here the concentration changes with distance. Let us say maybe the concentration will be something like this if this is the distance x, right. So, concentration versus x. So, why is that of importance? Because here when the concentration of the relevant compound is high, the rate of loss will also be high, and here also it is not at 10 milligram per liter. So, rate of loss is still high, maybe not as high. Only at the fag end of the bottom reactor will we have rate of loss to be low, because the concentration of A is low, right. So, only within a small zone of your plug flow reactor will you have low rates which are comparable to the rates which typically exist throughout your system in the CSTR. So, here we see that the rate of removal is higher, right, or in greater parts of the particular plug flow reactor we have higher rates of removal compared to the CSTR, right. So, that is why we have better removal with plug flow reactors for the same theta, meaning same V, right. When we say same theta, what is it that we mean? We mean that for a given flow rate, volume of both the reactors are the same. So, we see that plug flow reactors are relatively more efficient. Again, keep in mind that these are ideal case reactors, as in we are assuming that there is no dispersion here in plug flow reactor, or we are assuming that it is instantaneously diluted and so on and so forth. So, we will look at these aspects, but I believe I am out of time. So, we will look at these aspects in the next session, and I thank you for your patience, and I will end the session now.